Okay. We got here is a little problem I came up with involving baseball. I kind of wanted to put a little spin on the uh, lump of clay problem. So what I have here is a guy hitting a baseball straight out to center field, and the outfielder kind of just in desperation throws his glove in the air when he realizes it's going over his head. And the idea behind this is the ball is supposed to land in the glove, and the ball and the glove come back down and land in your lap. Um, People try this all the time in high school. Never works, but thought it was a cool idea. Um, for my vector, I kind of looked at the field of play, I guess you can say, in an overhead view instead of from the side like I have it drawn here. Um, it was just an easier way to think of it, so I used my x values as 0, and I use the y value as the I guess you know straight from home plate to center field, and the z value as from the ground to the sky. So you can see that neither ball nor the glove have any x value because the ball is going straight out to center field and the glove is going straight up in the air. Um, well, the ball is actually falling in a little bit, as you can see here. It's starting to arc, so I got -2. I calculated all of these numbers, made sure they were somewhat realistic. Um, I used meters per second. I figured 40 meters per second is close to 90 miles an hour or so. And I looked up these values for the weights of the ball and the glove. So to find the velocity of the ball inside the glove right after contact, um, we set up this formula VF, this final velocity, is equal to m1 v1 plus m2 v2. These are both initial values, the velocities, over m1, m2, which are the both of the masses combined. So I worked out my calculation. This is the answer that I got here in vector form, and you can see it is pretty believable. Of course, you're still going to have a 0 value for the x, and since the glove does weigh a lot more than the ball, um, you're going to have a much more impact from the direction the glove was traveling in. So when the ball hits the glove, it slows down its velocity from 40 to 9.3 in the y direction, and the glove actually speeds the ball up straight in the air um, substantially. So it's kind of believable if you think about it, what would actually happen if you did that. Um, so we got the change in momentum of the baseball glove alone. You're going to start with P1 and P2. P1 right here being this value here, and your P2 being the um, let's see, yeah, 120 times this initial value here. So you got your weight of the baseball times this value here, which is the final velocity. And I did all the calculations there, and this is the number I came up with. Uh, Again, it seems pretty feasible. Um, I think I made all my numbers very realistic, so it came out very believable. And of course, the unit vector, F net equals delta P over delta T. So you're finding the force of G on B, which is force of the glove on the ball. Um, so there we have it set up. Delta T is just going to be 2 since you only have two um, values, two different points that the momentum is measured in. So you find the magnitude and then F hat, and there you got it. Um, when I took the test, I was came up blank on all this stuff, but once I looked at the textbook, this here seemed pretty interesting, and I can actually understand it pretty good. And also this The unit vector part, still not too sure of. Hopefully, I won't have to do another reassessment.